It's recording. Okay. So, why? Since I've done this. Okay. So, the first question is, but the first question is, what are the products of a strong acid, strong base reaction? So, do you know?
Yeah.
Do you remember that?
Yeah. Just water and a salt.
Yeah, that's exact. Water and a salt, always. So, if you have the most common one that they like to do is NaOH aqueous plus HCl. And it's a reaction arrow because it's not at equilibrium. It's just going to completely react. And it's going to form NaCl in water. Yeah. So next, what is the acidity / basicity of these salts? I'm looking at it now and I'm realizing that like I gave the answers for part of them, but that was like supposed to be like a hint for me to remember. Then I forgot to take it off. So okay. But NaCl is what would be the like pH, like about like what pH would it be if I had like NaCl and I dissolved it in water?
Well, it's neutral, so it'd be close to 7, right?
Yep. So this one here is neutral. And then NH4Cl. Huh. It's gonna be acidic, like I wrote. What about KBr?
KBr would be. It's gonna come. K.
What do you think its conjugate acid / conjugate base are? Like, what reactants formed KBr?
It would be KOH and
Okay. KOH plus what? So KOH is what? Is it an acid or a base?
That's an acid. No, that's base.
Okay, so if you have a base, then you need an acid. So what makes something an acid?
HBr, right?
Yeah. Okay, so now that you know what it is or what your reactants are, what is the, I guess, like strength of these acids / bases?
They're both strong, right?
KOH and HBr. Very strong.
Okay, then it would be neutral again.
Yep.
So they both come from strong.
And then LiF. Do you know why lithium fluoride is basic? Why it would form a basic solution?
So no, I do not. Well, it'd have to be because it comes from a weak acid and a strong base.
Yeah. Okay, so you know, like your is it alkali metals? They form strong bases, and then you have HF, and HF is a weak base. I mean, weak acid. Sorry. Like the interesting thing is that like you would expect it to be kind of like very strong because like F is the most electronegative, but that's not the case because size trumps electronegativity. So like the bigger halogens are like a lot stronger in like acids than fluorine, because like the bigger you are, the more likely that you want to keep your electrons and give away a hydrogen. So that's why this is basic. And then the same thing applies for E, that you have this thing here. I don't know what it's called. I should have looked it up, but I can't remember. Yeah, it's a weak acid, or it's from a weak acid, so it's gonna form a basic salt. What about KNO? Oh, basic. But do you know why? Why is NO2 not strong? Like, isn't there a strong acid that looks very similar to like HNO2? Do you know?
Well, HNO3 is strong, right?
Yep. Yeah. But it's like it has to be very specific. Very specific. Like it has to be like, you can't do like what's another one? SO3. Like H2SO4 is strong, but H2SO3 is not at all. So it really does matter. So it's like, remember your strong acid, strong base, because then everything else is weak. So,
yeah.
What about NH4 and F?
So that would be. Hold on. Well, the F would be the HF. I know that part. And then the NH4 would be
so HF lost the hydrogen. What happened to NH4?
It would gain it.
Yep. So what would that make it?
NH5.
Are you sure?
It would gain the hydrogen? No, it's losing it. So it's
no. Yeah. These are your reactants. So your reactants gained, this one gained, and this one lost. Yeah.
Okay.
So what kind of solution is it going to be? Do you have any idea?
It's going to be
you know the KAs?
It should be acidic, right?
Because the Ka of HF is 6.6 times 10 to the negative 4, and then the Ka of NH4 is 5.8 times 10 to the negative 10. So what kind of salt is it going to be? Based on the Ka. So you know, if the Ka of one is bigger than the other, that means the Kb values like switch. So like the Ka of the Kb of HF would be smaller than the Kb of F minus. I'm sorry, would be smaller than the Kb of NH3.
So it'd be
basic. Cool. Okay. So, what is the pH of a 1.53 solution of LiF? That's a very good question. So, what's the first step?
The pH of a, let me look. Your first step is to break it. You would break it down, right, into the ions?
How? Okay, so I start off with LiF, and it's aqueous. plus what?
Do what?
Okay, I get what you're saying. So you do break it up into your ions. So in this case, you're just gonna kind of ignore like this. This happens. The reaction itself happens in water, but because like it's just water is on both sides, so
Yeah.
it's not really gonna react. You can just ignore it. So here you
Okay.
go, and then you got your F minus. So what's next?
You would.
Okay. So what is Li or lithium plus a part of? Like what was its reactant that caused it to create LiF?
It would be to create LiF.
Yeah.
So it would be LiOH and then
Okay.
HF.
Okay, so how is LiOH a strong base?
Yes.
Okay, so you can pretty much ignore the lithium ion without HF. Is it a strong acid?
No.
Okay, so you're going to carry this over here, and it's going to have another reaction. You got F minus aqueous. It's going to react with what?
Would it just H3O?
Are you sure?
I don't know. I think it's H3O.
It's the one thing that's all around. It's everywhere.
Oh, water.
Yeah.
And then it makes H3O.
Is it?
Right?
Are you sure? So it's a base.
No,
so what's going to happen?
So it would make OH and HF.
Yes. So what's next?
Then you would do an ice table, right?
Okay. So you got ICE. So it says that your initial concentration is 1.53. So do you think that 1.53 is also going to be the concentration of the fluorine ion or not?
No.
Why not?
Because it's the concentration of the solution as a whole.
Okay. So let me get rid of that scratched out. So this is your concentration of LiF. This is how much LiF you have in this solution of water. And okay. So this is LiF, is it soluble in water? Is it gonna completely dissolve in water?
I guess so, yeah.
Yeah, it will. So if it completely dissolves in water, you can pretty much just ignore the LiF part because it doesn't exist like this in water. So what would be your concentration of lithium then? If your concentration of LiF is 1.53.
I don't know.
Okay. So your concentration of lithium fluoride is 1.53. So if it breaks apart, that means you're still, how many, like, what is your mole to mole ratio between LiF and lithium?
It's just 1 mole each.
Okay.
So it would be the same, right?
Yep, it would be.
Okay.
So you got 1.53 molar. Water does not count. And then you got 0, 0, minus X, plus X, and plus X. So now bring it down, 1.53 minus X. X, and X. So what's one important thing that we're missing?
The Ka value? No, the Kb value.
Yeah, I mean, once you have one, you can get the other.
Mm-hmm.
So I wrote it up here. So the Ka of HF is 6.6 times 10 to the negative 4. So in order to get the Kb value, you take 1 times 10 to the negative 14 and divide that by 6.6 times 10 to the negative 4. And you get, as a Kb value, 1.5 times 10 to the negative 11. So now you can continue on. As you know, Kb. Oh, did you have a question?
Oh, no, I was just going to say what was next.
Okay, yeah. Good. Great. So HF. Oh, sorry, not plus. Yikes. OH minus over the F minus. So that is, I don't think I left myself enough space. 1.5 times 10 to the negative 11 equals x squared over, because the Kb is so small, you can ignore the x, so just 1.53. Cool.
Mm-hmm.
So now you have x squared equals 2.32 times 10 to the negative 11. And then you take the square root of that, and you get x equals 4.8 times 10 to the negative 6. Good. Did you get that?
Yes.
Or anything similar? Cool beans. Okay. So how do you find pH?
pH, you would take... You have to, let me look at my notes.
So what do you have here in the problem that you can get, or what is X?
Oh, you can.
What is X symbol?
It can be POH.
Yep.
So you
can find pOH.
Mm-hmm.
So here's your OH minus concentration here. It equals 4.6 times 10 to the negative 6. And you can find pOH by taking the negative log. So pOH equals negative log of your OH concentration. And then you're going to do 14 minus pOH equals pH. So what did you get?
I'm still typing it in.
Cool.
I got 8.69.
Nice.
Okay.
So 8.69 is your pH. Great. Okay, so next question. How do you make a buffer solution?
You would.
What is required?
You need it's base plus an acid and then 2 H2O. Wait.
Are you sure? What kind of base? What kind of acid?
It would be a weak. Wait.
Are you sure?
Let me. Okay. A weak acid or base in its conjugate.
Yes.
Okay.
Just wanted to make sure you're sure. Yeah. So So that's how you make a buffer solution. I don't know why I have this taste there. So also, what ratio, like, what's the best way to ask this question? What ratio of weak acid to conjugate base, or weak base to conjugate acid, what ratio is the best? Like, what is the best ratio of the two for the strongest buffer you can possibly get? No,
It would be 1 to 1, right? Just
yeah.
even.
Yeah. So the closer that their concentrations are to each other, then the better off that you're going to be.
Yes.
And also, at what pH do buffers work best?
Well, like within the buffer range, is that what you mean?
Yeah. Yeah. So do you know what the buffer range kind of surrounds? What value?
All I have written is that it would need to be, like, the base acid ratio should be under 10 and above 0.1.
Yeah.
Okay.
Okay. Well, I don't know if you guys went over this. Can't remember. But the best, like, range, like the buffer range is around the pKa value of the buffer. Like, if you had a pKa of like 9.4, you wouldn't want, like, I don't know, you wouldn't want to use something too acidic that would bring it down too low, because then it's not going to work anymore. You killed your buffer. Yeah. So, for the following reaction, I keep adding space. How will adding 1 m of HCl shift equilibrium? What's going to happen?
It would increase, so it would increase the amount of acid.
Okay.
Make the base acid ratio lower.
Okay. So which way will equilibrium shift?
It would shift. It would shift to the left.
Why?
Because there's more of the acid.
So what concentration is it increasing? When you add HCl. Which one? Yeah.
In this equation.
Yeah. Oh, sorry. Yeah.
Wouldn't it just be the H3O?
Yep. Because H3O is your stronger acid, so that's what it's increasing. Your H3O, so it's going to shift equilibrium to the reactants. Okay. So what effect will this have on your Ka value? So your Ka is H3O plus NH3 over NH4. So what will this do to your Ka value?
Will make it bigger.
Will it?
It should. Because there's more H3O. So the top number is going to be bigger.
Are you sure?
Yes. I think
no.
No.
No. K values don't change.
Oh,
never.
Okay.
Yeah, it was a trick.
Or
maybe it wasn't a trick when I wrote it. Like, maybe when I wrote it, I thought the wrong thing. And then I'm reading it now and I'm like, it doesn't affect it at all. So, yeah, it doesn't, because Ka values, they don't change no matter what. Okay. So, if you increase your H3O plus, this is the NH3 is going to decrease and the NH4 is going to increase. So, it's going to be proportional. Yeah. And what about if I add 1 molar of NaOH? Which way will it shift equilibrium? This one's tricky.
So that would increase the NH3 concentration, right?
Why?
Because that one is the it's the base and the reactant side.
This one's tricky because of the fact that your NaOH is going to react with NH4.
Okay.
So it's going to decrease your NH4 concentration.
Okay.
And if your NH4 concentration decreases, which way will equilibrium shift?
To the right.
Are you sure?
Oh, wait. Let me think. Yeah, it should shift to the right.
So you're saying that if I decrease NH4 concentration, it's going to shift towards products, further decreasing NH4 concentration.
No. It's going to shift to the left, so.
Yeah.
Okay.
Cool. I hope I'm still solid at this. Everything's fuzzy. Okay. So, which of the following buffers would be the most effective when using 0.1 molar of HCl? So HCl is a strong, it's going to completely dissociate. So which one's the best? Okay, so 0.13, what's that called? Acetic acid plus 0.01 m acetate.
So
you got what's your ratio between this one?
Between
a
those
one, a 1 to what ratio? Or sorry, what? So what's the difference between 0.1 and like what factor?
It would be 10 by a factor of 10.
Okay, so you got a 10 to 1 ratio.
Mm-hmm.
Okay, so what about NH4 and, well, 0.1 m NH4 and 0.01 m NH3? What about that?
That's still 10.
Yeah. And what about 0.1 m HCl and 0.1 m Cl minus?
That's 1 to 1.
Okay. And what about, again, the same 0.1 acetate and 0.1 0.1 acetic acid and 0.1 acetate?
That's still 1 to 1.
Okay. So which buffers are going to be more effective just based on their concentrations, not based on anything else?
C and D.
Okay. So you can cross out A and B. Okay. So let's look at C. What is HCl?
HCl is a strong acid.
Will it form a buffer?
So you need
It's going to form a buffer.
No, it shouldn't because it's strong.
Yeah. So like if you add 0.1 like M HCl and 0.1 Cl minus, what's going to happen is that all your HCl is just going to immediately become Cl minus, like immediately. That's just going to dissociate. So you're not going to have anything. Okay. So what about D? So you got CH3COOH and CH3CO minus.
Yeah, that one should form a buffer.
Yep. Actually a pretty common buffer to form. I don't know, you guys, they like changed the labs for you guys? Because you guys used to do a lot of like buffer labs and it was like all the time. Like reading the burettes and getting headaches and it's like, oh man, your numbers are bad. Getting an 800% error and stuff like that. So, oh man, the days, those were fun. All right, so the next question is calculate the pH of a buffer solution of 0.25 m NH4 and 0.1 m NH3. Okay. So what formula do you need?
You need to write OH minus plus H3O plus yields 2H2O for the SRF table.
Do you?
Oh, wait. Maybe not.
So you got a formula. I don't know what major you are.
Oh, I'm exercise science.
You probably never need to see this formula ever again, which you
No.
know is great.
Yeah.
So amazing. Because if you were a chem major, it never goes away.
Oh, it's the pH equals pK plus log. Is it that?
Yep.
Okay.
Henderson Hasselbeck. It's your best friend.
Okay.
pH equals pKa plus log of A minus over HA. So which one is A minus?
NH3.
How do you know that?
Yeah, because it lost the hydrogen.
Yeah. So like a lot of people, they see A and they're like acid. No, that's not right. It's your base. Okay. So your PK or you don't have your pKa, but you have your Ka.
No.
So we can solve for pKa by doing negative log of 5.6 times 10 to the negative 10. And the pKa is 9.25. Okay. So you can plug that in. You have everything you need. Plug it in first. So you want to determine the pH of your buffer solution before you add in any kind of acid or so that pH equals your pKa, which is 9.25 plus log of what over what?
It'll be 0.1 over 0.25.
Okay. And that is going to give you Did you get a number?
Yeah, I got the final answer or the log?
The final answer.
I got 8.85.
Okay. So judging by the concentrations, one way that you can know, there's like a trick so you can know whether or not you determine the pH correctly. So how, like which is in greater concentration, the acid or its base?
The acid.
Okay. So so pretty much the buffer has more acid than base. So what do you expect the pH to be in relation to the pKa if you have more acid than base?
Then it would be acidic. So it's going to be above 7.
No.
Oh, wait. No.
If it's you're just saying that in relation to your buffer, it's more acidic than your buffer.
Yes.
So that means the pH should be lower than the pKa if you have more acid than base. But if you have more base than acid, it should be greater than the pKa. So that's how you can kind of know whether or not you did your calculation right. Like if it was 0.25 NH3 and you got 8.8, that doesn't make sense because that means your pH is lower when it should be higher because there's more base than acid. Whereas if it was an equal concentration, pKa equals pH.
Okay.
Yeah. Okay. So what's going to happen after you add 0.05 molar of HCl?
You would take in the ratio part, you would subtract 0.05 on the top and then add 0.05 on the bottom.
Are you sure?
Yes, because HCl is acidic.
Are you positive?
Yes, I'm pretty positive.
Okay. 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 Sorry. I was just thinking, I was like, wait, did I forget to include the volumes? I'm pretty sure that's important because don't you need it for your SRF table, right?
Yes, you do.
Yeah. Let us assume right here, officially on this video, that the NH4 and 0.1 NH3 makes a 1. I'm trying to figure out where to write this. 1 liter solution. So
Okay.
that is an L, not a 2. Do my L's weird, but for the sake of this video, I'll do L different. So 1 liter solution. And let's say that you're adding 10 ml of HCl. Okay, so now we're all fixed. We're all good. Everything is perfect. Okay, so what color? What's next?
You need to change things to moles to make the table.
Yeah. So what are your moles of NH4?
Of NH4.
Yeah.
It would be it would just be 0.25 because it's just 1 liter. Is it just 1 liter?
Yep.
Okay. Yeah, it'd just still be the same since you're just multiplying by 1.
What about NH3?
It would still be 0.1.
Okay, and HCl.
HCl is just 0.0. Oh wait, it would be point. It'll be 0.0005.
Yeah. All right. So now up your SRF table. The next most important thing is knowing what goes where. So what's your equation going to look like?
It's going to be the OH minus plus H3O plus yields the 2H2O.
No.
Right? Oh.
Is that what you guys learned, how to do it?
Mm-hmm.
In this case, it doesn't quite work.
Okay.
So what is going to react with the acid? NH3 or NH4?
The NH4
is going to react with the acid?
Yes.
And what would it make? So you want NH4 or NH3 to react with something to get the other. So you'd want NH4 to react to become NH3. Mm-hmm. So would it react with an acid to form NH3?
No, it'd react with So
what's reacting with the acid?
A base.
Yeah, which is
the NH3.
Yeah. So probably should have paid attention more in class because I'm not sure I remember her doing the whole H3O plus OH gives you H2O. I understand it a little bit, but like in terms of like determining your conjugate base, or in this case, I wrote the wrong thing. In terms of finding your conjugate acid, in this case, which is NH4, it would be kind of confusing. So, like, I hope this doesn't confuse you, but it's going to be your NH3, which is going to react with your HCl. But in this case, you can just kind of, you know that once you have HCl in water, it's just going to completely dissociate to H3O plus. Yes. Okay, so it's going to be H3O plus is going to react. It's a reaction. It's not equilibrium. Gotta make sure I remember that. To form NH3 and water, which is a liquid, so it doesn't count. So now I'm going to do the SRF. F and then C. Okay, so what are your moles of NH3?
0.1.
Okay, so 0.1 mole. And, oh, I wrote NH3 twice. That is my bad. NH4 plus. Okay, and what about your H3O plus?
That's the HCl moles, right?
Yeah.
So the 0.0005.
Yeah, you can use H3O plus, or you can also just use H plus, because you know that the Cl minus isn't going to do anything. If you just want to use H plus, that also works. Like whatever your preference is. And then your NH4 concentration is 0.25 moles, and then H2O doesn't. Okay. So I can't remember. It's reaction. Oh, no. H3O does not go here. No. It goes. Okay. So how much is the NH3 concentration gonna change by? Do you know?
I'm not sure.
Okay. So you're reacting, it's I guess your clue kind of comes from the equation. So you know that your HCl is going to completely react. Like there's none of it's going to be left. So if HCl completely reacts with NH3, what are the moles of NH3 going to change by?
Moles, if it completely reacts, so it would just be.
Yeah, because in acid-base reaction, you're relating moles to moles. So moles will react with moles, like 1 mole will react with 1 mole. 1 mole of acid reacts with 1 mole of base. So what will the change in the NH3 concentration be?
It would just be minus 0.00.
I'm pretty sure you said it.
Yeah.
Cut off 0.05 mole. But yeah, like pretty much whatever your acid or base is going to completely react. So the only time the acid or base that you add, because you're only going to add a strong acid or strong base in these kinds of reactions. So the only time it's not going to completely react is that if you have too many moles of acid or base. Like you have more moles of acid, like strong acid, than you have of like the weak base that's in the buffer. That's the only time. So it'll completely consume it. And that's the only time that like it won't completely react. But either way, you're still gonna subtract one from the other. Like you're gonna completely like take all the acid that you added or all the base that you added and like subtract it from the other thing. So I think this is 0.005 up here. I can't either way, you'll get to the same answer. So oh, and I'm pretty sure you said minus also. So what about for NH4? Plus or minus?
Plus.
Yeah, because its concentration is, and you know why the NH3 concentration is why it's minus moles?
Do
you know why the NH3 is losing moles?
Because it's reacting with the HCl.
Perfect. Okay. All right. So I don't know what 0.1 minus 0.0005 is. It is 0.0995. And this is going to be That's going to be completely used up. So you're not going to have any more H3O, maybe 0. And this is going to be 0.2505 mole. Okay, so how do you find your new concentration?
You would set it equal to the Ka value.
Are you sure?
Just do
How do you go from moles to molarity?
moles to molarity. You just divide by liters.
Okay, so what's your volume now?
It should be 1 liter plus the 10 milliliters.
Yep.
Like 1.01 liters.
Alrighty. So take your 0.0995 and divide by 1.01, and you get, I think I did that right. 0.0985 m. And if you do the same thing, 0.2 by 1.01, you get 0.248 mole. Big M. Okay. So what's next?
So you would plug that into the pH pKa equation.
Yep. The Henderson-Hasselbalch. So
Yeah.
you got your pH. Oh, it does this so hard. Jumps out of nowhere. pH equals pKa plus log of your A minus your HA. And your A minus will still forever be your base. It doesn't matter whether or not you're adding acid to the buffer, adding base to the buffer, whatever your conjugate base is, it goes at the top. Will never change. It will never, ever, ever, ever change. It's always A minus over HA. Like always. Just remember that. It will never change. Ever. Okay.
Okay.
Just wanted to say that. So 9.25 plus log of 0.0985 m over 0.24. Oh, no. Sorry. I was supposed to add. Oh, no. What am I doing? Sorry. Haha. I did add. I was looking at the concentration. Okay. I confused myself. I was like, oh, I did it wrong. Because I used to, every time I did Henderson-Hasselbalch, like I used to always either add to both or subtract from both. So that's why I was like, no, I can't do that again. All right. Okay. It's looking good. So now pH is going to be what'd you get?
I got 8.84.
Okay. You got 8.84. What was the pH of your buffer? Was 8.85. See how tiny of a change that was? It was like almost non-existent. Yeah. And then you can also look at your pH again to see whether or not it makes sense. Like if you add acid to your buffer, should the pH go up or down?
It should go down.
Yeah. So you can tell like, oh man, I shouldn't do that. All right, and one other small, tiny thing is I don't think she taught you this, and I hope that me telling you this does not negatively affect you in any way. I really hope it doesn't. But you technically do not need to find the concentration.
Okay.
You can just take your moles straight and plug them in, and you'll get the same exact number every single time. And the reason for that is that you're going to have log of 0.0995 moles over 1.01 liter over 0.2505 moles over 1.01 liters. So your liters are going to cancel because they're going to be the same volume. So liters technically do not matter. If you want a shortcut and you're on the test and you're like, man, this is a lot of calculating, and you're like, oh man, now I got to find the concentration. And like, if you get confused and you're like, oh man, like, what is the concentration? You don't need it. Or I mean, yeah. Like, what is the volume? If you get confused and you're like, oh man, what's the volume? Or if you know you're likely to mess up with the volume or like to forget that the volume increases, just don't use it because you'll get literally the same number.
Okay.
Like, that was one thing that I learned from all of like the titrations that we had to do. The titration, buffer titrations. Like for the equation that they gave us, it was like log of moles over moles. So I was like, oh, cool. You don't have to use concentration. Hope that does not hurt you. Hope that only helps you. I really do. Because if it hurts, I'm so sorry.
No, you're good.
But it's supposed to help. Okay. And then if I add NaOH, it's past 3:30. So I'm going to try to do this quick for you. So NaOH or OH. Yes, that's what I'm trying to say. OH is going to react with the acid or the base.
It should react with the acid.
So you got H plus the OH minus is going to give you NH3 plus H2O. You got SRFC, and you have your original still 0.25 0.25 or 0.25 mole. And you got 0.00 because this is, let's assume this is also 10 ml, so 0.05 mole and 0.1 mole, and this never matters. And then it's minus minus 0.0005 mole, minus that as well, all these zeros, plus 0.00, and then it's going to be 0.25 minus 0. So we're going to have 0.2 or 4.950, and then 0.1005. So this time we're going to do it without the concentration because you don't need it. Like when I learned the SRF table, it was just SRF. Like there was no C at the end, just SRF. That's why like even you call it the SRF table because like the C wasn't always there. Yeah. You know? So you could do your pH equals your pKa plus log of acid moles, base moles over acid moles. And you'll get, so you do the log 0.105 divided by 0. So when I calculated it, I got pH equals 8.8. Oh wow, 8.86.
Mm-hmm.
So, and it went up because you added base, so that makes sense. And you would have, if you want to try it out by doing the volume, you'll realize you'll get the same exact answer every single time. So just in case you don't trust me, you know, like, but always feel free though to like always check yourself, because you don't want to get like a failing grade because somebody told you the wrong thing. I make mistakes too, and I'll feel really bad. Okay, so this one's a little simpler, I think. Yeah, it's just the pH of a buffer solution. So how do you find the pH of a buffer?
You would
Best friend, your favorite equation.
Yeah, you would just use that equation again.
Yep, Henderson Hasselbalch. pH equals pKa plus log of your A minus over HA. Okay, so I think acetic acid is negative log of 1.75. Yikes. Yikes. E-5. And I realize I keep using the same things over and over and over again, and that is because of the fact that when I took the lab for this class, these were the two things we constantly use, no matter what. So I don't know why. It's like ingrained in my brain. So I'm like, why like try so hard to think of like another like substance when I could just use what I know? That's what I did.
Yeah.
So the pKa is 4.76. Now I have a question. What are you gonna do with this? Does it matter? You need to do anything with it? The 0.53 liters.
It shouldn't matter because you can do it with concentrations.
Are you sure?
Yes.
That's fantastic because you're perfectly right. Like, it's just, you know, like when you get extra information and somebody's like, I don't know how to do it anymore. And I'm like, no, it's still the same thing. So yeah, it's great. Oh, no. Okay. Wait. This was the trick. I forgot what I did. This is not a buffer yet.
Oh, okay.
Yep, it's not a buffer yet. You need it to be a buffer, so we'll go down here and then come back. Okay. So you got. So you do need the volume.
Yeah.
Whoops. I didn't read it. Okay. That's why I usually. Okay. So now, what you got? You got NaOH. This is going to be a reaction. CH3COOH. Yes, that's right. Okay. We're going to react to form what and what?
It would make CH3COO minus. And then.
Yep. And if it helps, you can just ignore the sodium.
Okay. And then it would just make water, right?
Yep. Okay. So now you can still do your handy dandy SRF because of the fact that when you're doing any kind of acid-base reaction, you're relating moles to moles, not concentration. Because 1 mole of acid will react with 1 mole of base. It doesn't matter whether that's a weak acid or weak base, either one, it'll still be 1 mole. So we're going to use our liters that I said we wouldn't use, but we're going to use it anyways. So 0.03 divided by 0.53 gives you 0.06. I'm just going to round moles. And then 0.1 divided by 0.53, 0.19 mole. This is just 0, and that never matters. SRF works just the same. So all of your what is reacting or what is less is what you're going to subtract. You're going to subtract the lower thing by the lower value. So you have less OH. So you're going to subtract 0.06 mole. And you're going to add 0.06 mole to get 0 NaOH. That's all used up. And then now you have your buffer concentrations. The concentration for your buffer? No. Yes, your buffers. No, you don't have that yet. Sorry. You have the moles. That's all I'm trying to say. Okay. So now you do need the C. Do you? No. Yeah, you do. No, you don't. You don't. Okay. Haha. You never need the C. I don't want to be like, oh, you never need it. And it's like, yeah, you do. And then you're like, oh man, but she told me. Okay. So now we can take these beautiful numbers and go back up here. So it's what over what?
The 0.06 over the 0.13.
Okay, so now we can do our calculations. So you got log 0.06 divided by 0.13. That's 4.76. And your pH, what'd you get?
4.42.
Perfect. Oh, sorry. I meant to put 4. Cool. So that's it. What was I gonna say? Okay, does this make sense? Does it make sense that your what am I trying to say? That your pH is lower than your pKa. Does that make sense?
Because it's adding the NaOH, which is basic.
Are you sure? That's why.
Weight is getting lower.
Yeah.
No, it's because there's a higher concentration of the CH3 COOH, right?
Yeah.
Okay.
Yes, absolutely. That's why. So you can like you're going through your test and you're like, oh man, does this make sense? Does it make sense that the pH is smaller? And you're like, oh man, yeah, it does. Because I have more of the acid than I do of the base. So it's like, perfect.
Okay.
That's all I got for you.
Okay.
I hope that